All right, 4.3, monotonic functions and the first derivative test. All right, so a function that is increasing or decreasing on an interval is said to be monotonic on the interval. So that's all we mean by that. So then we get into a corollary. Suppose that if, not that if, suppose that f is continuous on the closed interval a, b, and differentiable on the open interval a, b. All right, so it says if the derivative of f or f prime is greater than zero at each point of x that's in the interval AB, then f is increasing on the interval AB, the closed interval AB. Now, if f prime is less than zero, so negative, if f prime is greater than zero, is positive. If f prime is less than zero, that means negative. At each point of x that is in the interval AB, then f is decreasing on the interval. So when you talk about a graph, just generically, so if I have this point right here, this point right here, it's increasing up to this point, decreasing down here, and then increasing up here. So that's what we're talking about, the intervals in which your graph is increasing, decreasing. And remember, I told you, I mentioned to you last class that we're going to take a bunch of information and be able to draw the graph without actually using a graphing tool. It's called curve sketching. So,
Yeah, it's just meant to be a general outline of how the graph moves, right?
yep, yep. All right, so let's see. Am I missing one? I think I'm missing one of my. Maybe it comes after this. Yeah, it comes after the example. Okay. All right, so find the critical points of f of x is equal to x cubed minus 12x minus 5, and identify the open intervals on which f is increasing, f is decreasing, oh, increasing, and f is decreasing. Okay, so first thing we need to do is find these critical points. So we want to figure out where f prime is 0 or undefined. First thing we need to do is figure out where f prime is. So that x cubed will turn into 3x squared, and that 12x would just be 12. And of course, 5 is a constant, which goes to 0. Now I set f prime equal to 0. So I will factor that out. 3x squared minus 4 equal to 0. That's 3x plus 2, x minus 2 equal to 0. Then set each piece equal to 0. Have negative 2 and positive 2. All right. So what we're saying here is that we have our critical points, or in other words, our extrema. And so our graph is going to respond a certain way within these intervals. So it's going to be either positive or negative in this interval. Every value will be positive or negative in this interval. Then in this interval, it would be the opposite. Well, normally. And then in this interval, it would be the other. That's normally the case, but it doesn't necessarily have to be that way. And that's why we still have to do our test values and check. So we have these intervals here. Let's see how I want to start my. Let's go. got our intervals. So if we were to take something simple like a parabola and do this, and this is what I mean. If I look at right here is where my graph is equal to 0. We can have it. This is just an example of what I mean by our graph behaving a certain way. As a matter of fact, I won't even use a parabola. I'll go back to the graph I used before. And we're looking at critical points. So we're talking about increasing and decreasing. So all the way up to this point is increasing. From this point to this point is decreasing. And then this point to this point is increasing. So what they're saying is that from this interval, when I plug it into my derivative, I'm going to get positive values. For this interval, when I plug it into my derivative, I will get negative values. No matter what, as long as it's in between these 2 points, I will get negative values. And then from this point on to infinity, I will get positive values when I plug it into my derivative. All right, so the intervals we have is from negative infinity to negative 2. Yeah, we're dealing with open intervals. And then we have negative 2 to 2, then 2 to positive infinity. You can choose anything in that interval. So negative 3, yeah, I choose 0, and positive 3. I could have chose negative 100 for the first interval, 1.5 in that second interval, positive 1 million in the third interval. Doesn't matter what you choose, as long as it is in the interval, it will still represent what's going on in that interval. Just remember, whatever you choose, you're gonna have to calculate with it. So f prime of x is 3x squared minus 12. So this is a simple one to plug in. Take our test values. So result is positive because I got a positive 15. So I'm just doing generically because remember I said you didn't have to choose negative 3, but the result should have been a positive value. So I'm just going to put a positive there because that's the ultimate goal. Am I getting a positive or negative result? Plugging in 0.
And because it's positive, that's how we know the line is going up.
Right.
To the negative 2.
See, we get a negative right here. And then for that last one, and like I said before, just because you get, let's say positive, negative, negative, that does not mean you did anything wrong. You just have to make sure that you calculate it correctly. If it happens, then it happens. That just means that wasn't, you could have had a local extreme versus an absolute extreme, or what else? What's another scenario? It's just different kind of graphs out there that could actually result in that, but we'll talk about it when we come across it. And so we got a positive, negative, positive. So make sure you finish copying before I keep going. All right. So we would take that we see here. That means it's increasing on this interval, decreasing on this interval, increasing on this interval. And what they exactly they wanted from us, identify intervals and on which interval increasing, decreasing. Okay. So it's increasing from negative infinity to negative 2, 2 to infinity, then decreasing from negative 2 to 2. All right. Questions? Any questions? Make sure I get my stuff straight. All right, we got more to this, but I want to go ahead and read what we have before I write the rest. First derivative test for a local extrema. Suppose C is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing C, except possibly at C itself. Moving across this interval from left to right. That should be a comma. So, like we've been following our graph from left to right. Okay, so your three possibilities, if f prime changes from negative to positive at C, in other words, it's going down and then it goes up, that means you have a local minimum at C. If f prime changed from positive to negative at C, then there's a local max. So if it's going positive, it means it's going up. Then it goes negative, it goes down. So that means there's a local max at C. And then that third one is the scenario I was mentioning a few minutes ago. If f prime does not change sign at C, then there is no local extrema at C. All right, so want to find the critical points, identify the open intervals on which f is increasing or decreasing, find their functions, local and absolute extreme values. So let's look at f of x equal to x to the 1/3, x minus 4. All right, so we have x to the 1/3 times x minus 4. What I would probably do is go ahead and distribute that. All right. So I don't need to turn that black. So don't forget your exponent is 1 here. So when you go to multiply those two, you need to add your exponents. There's 3/3. 4/3. All right. So now we can find f prime. 4/3 x. Subtract 1 from x. I mean, not subtract 1 from x. Subtract 1 from 4/3. That'll go back to 1/3. Hold on. This should be a 1/3 right here. That's not erasing. Okay. Sorry about that. That 1/3, that x to the 1/3 should be in the back behind that 4. X to the 4/3 minus 4, x to the 1/3. All right, then here, bring the 4 down, 1/3, subtracting 1 from 1/3. So that'll be x to the negative 2/3. All right. So they went ahead and combined this. So let's see if we can do so. Right there. So you bring your exponent, that negative exponent down bottom. Now, if I want to combine these terms like they did in the book, just so, you know, just in case you were to see something like this, I want to multiply. I need to have a common denominator. And notice I have x to the 2/3 down here. That means I want to get x to the 2/3 down here as well. All right. So it means I need to multiply both top and bottom by x to the 2/3. All right. So here, whenever you multiply your variables, you add your exponents. So that'll be 1/3 plus 2/3, which would be 3/3, which is just 1, of course. So it's going to be 4x minus 4. Yeah, I can go ahead and just bring them together. So we have 4x minus 4 over 3x to the 2/3. And so they factored it all out. Do it like that. So, you know, it started off, you know, in this form, but, you know, when they put it in another form, we should be able to decipher, you know, what is what and how they got what they got. So just make sure you're careful of that. I just want to show you how they got here. And left off my 4. All right, so I need the spots where f prime is 0 and undefined. That's my critical points. All right. So when I look at and examine what I have here, if I get 0 in my numerator, that's when my function will be 0. If I get 0 in my denominator, that's when my function is undefined. So when we talk about fractions, don't forget that element. All right. So 0 in your numerator means the function is 0. 0 in your denominator means the function is undefined. And also undefined trumps 0. So what I mean by that is if you were to have both of them, let's say you have 0 in your numerator and denominator, then your function is undefined. So being 0 in your numerator in your denominator always supersedes everything. So I could have said it that way. 0 and so 0 in your denominator supersedes all. So we will do things because we get 0 in the denominator. It can alter our plans, make us rewrite problems because we got 0 in the denominator. 0 in the numerator is fine. You know, that gives us 0. That's an actual number, but 0 in the denominator is a problem. So looking at my function, if I look at my numerator to solve when it is equal to 0, all we're doing is looking at x minus 1 equal to 0. So x equal to 1 is one of my critical points. This is coming out of the numerator being equal to 0. Then looking at the denominator equal to 0. Divided by 3, that'll be x to the 2/3 equal to 0. Then you want to raise both sides to the 3/2 power. And of course, that is 0, but just going through the process, just in case you had another number other than 0, you're trying to figure it out. So you would raise both sides to the reciprocal or the reciprocated exponent in order to solve that. All right, so before we keep going, any questions? All right, so we do what we did last time. We can set up our chart. We got our intervals, test values, and then behavior of the graph. So we're going from negative infinity to 0, 0 to 1, 1 to infinity. So we want a test value. Anything less than 0, we can do negative 1. Anything in between 0 and 1 is 0.5. Something greater than 1 is 2. So we're plugging it into f prime. F prime is 4x minus 1, 3x to the 2/3. Plugging in -1. All right, so that's -2 on top. You take the cube root of -1 is -1, then square it is going to be +1. So that's -8/3. So we're looking at negative for the first one. All right, 0.5 to the 2/3. I'll just write the decimal. Well, bottom line, we see here, I really didn't have to do that. I can keep it clean. See, we're getting a negative value right here. And remember, that's our main thing that we want to establish. Are we getting a negative or positive value? So 0.5 is positive. So I am still going to get a negative right here. Then our next value is +2. So same things happen with that 2 raised to the 2/3 power. I can leave that the way it is because I just need to establish my sign. That's going to be positive. This one was negative. We saw that this one was negative. All right, so notice we have that scenario I mentioned when we have negatives in succession or back to back. So I'll let you finish copying that and then we'll look to finish it off. So both of those are decreasing. Then we have this interval increasing. So a few points from this, x equal to 0 is not a local, I don't want to say local extreme. Yeah. I'll just say an extreme. So x equal to 0 is not an extreme value. So our graph is increasing from 1 to infinity and decreasing from -infinity to 1. That's what we have here, is decreasing all the way to 1 and going up at 1. And we have all right. Questions on anything I've written. So x equal to 1 will be our absolute minimum. So that's how we will use that first derivative test. Testing for local extrema and increasing and decreasing intervals. All right. Any questions or concerns before we close this out?
No, I ain't got no questions.
All right. Sounds good. Sounds good. So that's it for today. Since I haven't posted that test, I'll try to post that tonight and watch your emails as far as class on Wednesday. And we'll go from there. All right. Of course, if you have any questions before next class, feel free to email me. I'm always checking it. And have a good one. And I will see you on next class, man. Stay safe.
Alrighty, you too.
All right.